speaker for tonight, Dr. Phil Jones. Dr. Jones is head of the Welsh School of Architecture at Cardiff University in the United Kingdom. And he's also chair of the Welsh Low Carbon Research Institute, which is a consortium of six Welsh universities working together with governmental and industrial partners to promote a low carbon agenda. Dr. Jones is going to be delivering this afternoon, tonight, a lecture entitled Towards a Low Carbon Future, From Buildings to Cities, Policy to Practice. So without further ado, please help me welcome our speaker tonight, Dr. Jones.
Thank you very much, and thank you for inviting me to speak tonight and to visit Ball State University. I'm going to talk about the work that we've been doing on low carbon built environments, and we've been doing this work for probably 20 or 30 years now. So we've been involved in the subject area a long time. I'm not an architect, I'm a building physicist. I always feel I have to apologize for that in some way. But my talk will be mainly from the point of view of building physics. And building physics is it's a growing area in Europe now, especially in Switzerland and Germany, where the building physicist is a member of the design team alongside the architect and the engineer and the project manager, etc. So it's an emerging discipline. So what I want to talk about is low carbon built environments, and I'll start by going through some of the drivers that make this subject area important. I look at building scale issues, and then I'm going to go on to more urban scale, and I'll be relating the talk to projects that we've been involved in or designs that we've been involved in at the school. So firstly, just to set the scene, in 2007, the Intergovernmental Panel on Climate Change came up with some statements. We're now 90% sure that climate change is due to human activity, and that we need to maintain global warming within 2 degrees if we're to avoid serious climate damage. And that means about 450 parts per million of CO2 levels. And at the time, they said we had 10 years left to avoid a chaos point. And it's interesting to note now that's 6 years ago. So I guess we've got 4 years left. We really have plenty of energy. It's just atmosphere we're running out of. And when I first started in this area, we were worried really about using up the energy and not having any energy to drive the planet. And that's changed over the last 20 or so years. Now we still have energy, but we don't have enough atmosphere to dilute the pollutants that's coming from burning our fossil fuels. So it's not energy we run out of, it's atmosphere. It's also interesting to note that the main definition of sustainable development, meeting the needs of the current generation without compromising the needs of future generations, was made in 1987. And that's, getting on for probably 30 years old now. So we've recognized that there is a problem for some time. And in 2006, there was a major report from Stern, the British economist, the economics of climate change, and that recognized that climate change is the greatest market failure the world has ever known, and that it's going to be far more expensive to put right the problems from climate change than to do something about it now. So it's much more economic to do something than to wait for it to happen and then clean up. So there are there's lots of information and reports to recognize the problems. And I don't want to dwell too much on the problems because I want to dwell more on the solutions. And the built environment is where a lot of the solutions lie. It's the key to sustainable development. We use about 60% of all materials in the construction industry, and we create huge amounts of waste. 60% of global timber products end up in buildings, and nearly 90% of hardwoods. 50% of water is used in buildings for sanitation and other uses. We compete with land. The buildings we build now are competing with agricultural land and other land uses, and we're losing land to the built environment at a rapid pace. And of course, energy, 50% of energy is used in buildings. So the built environment is key to sustainable development and key to the low carbon agenda. I said we've been talking about sustainability for some time, and I guess we've started to become concerned in the energy crises of the 70s. And we want to create now this zero carbon planet. It's been estimated that all the CO2 that we've put into the atmosphere since the Industrial Revolution, if we look at that amount, we've got the equivalent to put in again before we exceed this 2-degree rise. But we can do that very quickly, within 20 years probably, if we keep on at the rate we're going. So it's accepted at some time we need to get to a zero carbon planet, because once we've put all this CO2 into the atmosphere, it'll take hundreds, if not thousands of years to stabilize back out. To get to a zero carbon planet, we need a zero carbon built environment, and we need to reduce demand. We need to decarbonize the energy supply, and we need to do that at a building and an urban scale. Now, we started in the 70s with low energy design, and I remember the first projects that I was involved with were designing some housing to use less energy to inform the building regulations that were being developed in the UK at the time. And we looked at energy efficient design, we looked at increasing thermal insulation levels, increasing air tightness of buildings, and efficient heating and ventilation systems. Not so much cooling in the UK, but that was the sort of the main emphasis in the 70s in response to the energy crises of the mid and later 70s. And we designed a lot of buildings to these standards. Our building regulations pushed these ideas forward. But we ended up with buildings that rejected the climate and were pretty boring, small windows, thick walls, basically. And so we started to become interested in the 80s in passive design, looking back at the principles of how we used to design, and using the solar radiation, using daylight, using natural ventilation, and using thermal mass. And so these related really back to vernacular design in many countries. And then, I guess in the 90s, we started to become interested in sustainable design. The word sustainable development started to be used. And that expanded our sort of design principles, really, into what materials we're using, how we could use renewable energy, and also looking at the socio-economic aspects of building design. So linking the environment with social and economic aspects. And then, now we have what we term zero carbon design, where we take it even further, we take the energy efficiency further, we take the passive design further, we reduce our energy demand, we use more renewable energy supply. We're starting to be concerned not just about the heating and cooling and ventilation of buildings, but also about how much energy we use for appliances, electrical appliances mainly. And we start to think about how much energy is embodied in the construction of the building, as well as associated with the operating energy of the building. So that's really a sort of a quick history of energy sustainable green design. And of course, over that period of time, from the 70s to this decade, our CO2 levels have continued to rise, and our average global temperatures have continued to rise. So even though we've been doing something, it hasn't had much of an impact. We carry on in the same way, mainly. There's some really nice examples of sustainable energy design, but when it comes to the serious stuff, we just sort of push it aside. And this is what's happening in many parts of the world. And this is what we are starting to get more involved with, these sort of projects, as well as the sort of small and perhaps easier stuff to deal with. We have targets. We have lots of policy for sustainable development and low carbon development. In Europe, we have the 20-20-20 target. So by 2020, we want to cut greenhouse gases by 20% based on 1990 levels. We want to have 20% renewable energy, and we want to have 20% reduction in energy consumption. We have other targets in the UK looking longer. We want to reduce CO2 emissions by 80% by 2050. And most of our policy is based around this longer-term target. Although the way the government in the UK is going at the moment, we're probably going to be starting to do something about 2049. So they still have the 2050 target, but they're sort of pushing things forward. In Wales, we have our own devolved government now. Wales is a part of the UK, but we have responsibility for the environment and for other things like education and transport. We have, for the first time, our own building regulations, and we're trying to persuade, I guess, industry. The government is looking at 40% reductions in CO2 levels in housing. And if we don't get too much lobbying from the mass house builders and other parts of industry, I think this should be a reality soon. But also we have longer term targets. We want to be self-sufficient in electricity within 25 years. And we have lots of coastline. We've got an interest in tidal energy. We have wind energy onshore and offshore. We have biomass. And although it rains a lot in Wales, we have a bit of PV solar potential. So there are lots of targets, but it's how we get these targets into practice that's difficult. And what we've done with the university is that we've set up a low carbon research institute in Wales, and we have a partnership now with 6 universities, the government and industry, to drive forward this low carbon agenda. So we work with the government on policy and what they should be funding. We work with industry on the development and implementation of new technologies, and then the universities provide the research and training element. And this has been a very successful partnership, and at the moment we have a funded programme of about £80 million, with most of the major industries in Wales associated with that, including Tata, our steel industry, Sharp, our solar PV industry, and a lot of the construction industry as well. And we've developed a number of centres in Wales. We have our Spark, which is our solar PV centre, top right there, which has the largest thin film solar array, one of the largest in the UK anyway. We have a hydrogen centre where we're looking at hydrogen technologies. We have a gas turbine research centre where we're looking at gas turbines, and in particular carbon capture associated with gas turbines. We have our bioenergy, IBAS, that's looking at bioenergy in Aberystwyth. And in the built environment, in partnership with our steel industry, we have a Sustainable Building Envelope Centre. And I'll speak a little bit more about that later, where we're looking at using the building envelope to generate energy, both thermal and electricity. And in the built environment, we're looking at various scales. So we look at building scale, community scale, city scale, and up to regional scale. And we're looking across the demand and supply scenarios. So we're looking at reducing demand and also providing supply from zero, low carbon, and clean fossil fuel sources. At a building scale, there's a lot going on. This is a bedstead by Bill Dunster, who is who we work with on a number of projects. And this is quite an old project now, where it incorporates reduced demand with renewable supply. And the interesting feature is the natural ventilation wind towers, which recover the heat that's lost. And that's a sort of heroic project in the UK. It's one of the first major low-carbon developments. So we want to reduce demand, and we want to have renewable supply. That's the main focus of getting to low or zero carbon. And if you look at the design strategy that we use, in research and in design projects that we work on, we have a design practice in the school that designs buildings, and I'll show one or two of those as I go on. But the first thing is to reduce energy load, and that really means to reduce the lighting load, the load for appliances, to have good control over your internal loads. That's always the first part of low carbon design. Then we use the passive elements, the architecture of the building, orientation, mass form, fabric insulation, glazing, shading systems. And if we get that right, if we get those two right, then the HVAC systems, the heating, ventilating, cooling systems are much simpler, much smaller, and much more energy efficient. And then we have to look at the way we deliver the heat and cool to the space. And we now look at different ways of delivering, not with the air. We use a lot of chilled or heated surface systems now in Europe. And then, at the end of all that, we've got a smaller amount of energy to supply to the building, and then we can do that with renewable sources. There's more chance then of being able to take care of the whole building energy requirements from renewables, whether they're solar, PV, thermal, wind, biomass. But associated with that, then, we have to start to look at storage, because the sun doesn't always burn when you need the energy, the wind doesn't always blow when you need the energy. So the storage issue is becoming one of the main research areas now for us and others. So that's a straightforward, that's how we approach low carbon design. And you have to do that in a holistic way. You have to, when you reduce the loads, you use the passive design, you then save money because the systems are smaller. So if you do it in a holistic way, it needn't cost that much more. So some examples of what we're doing. These are two houses in Wales. As part of our push towards zero carbon buildings, the government have funded a number of demonstration designs. And these are some examples of houses which the heat loss is now down to 1 kilowatt. And just to put that into perspective, in Wales, design temperature is about -1, but it can get down to -5, -10 on occasion. So that's the sort of conditions that we design for. And these have solar PV, and of course, in the UK, like many other European countries, we have a feed-in tariff, so the government will pay for every kilowatt hour you generate. And so it's not a bad investment. It used to be much better a year or two ago when the government first launched the scheme, but so many people took advantage of it that they've sort of reduced the benefits now. So the early schemes were very good investments, 15+% return on investments. Now we're down to about 7 or 8%, which is still better than the bank. So these are some of the houses that we're building. We're also interested in building from local materials and getting the embodied energy down. And this is an example of a project that we're doing called T-Enos. It's in Wales a long time ago. If you built a house in a night, you could own the land. Not anymore. But so we've taken this idea about how you could construct a house very quickly from a panel system using local Welsh timbers. And we demonstrated this in Washington. There was an event, a Wales in Washington event, about 3 years ago. Not very sustainable to actually ship this to Washington. But it was a demonstration. And we're now using this system to build houses in Wales. And this is a project that we've done in the school. It's a near zero carbon house built with this T-Enos panel system using local timbers. We also use biomass a lot in Wales. We've got quite a growing biomass industry. And this is an example of a care home, which is heated by biomass pellets. And we now have what the government calls a renewable heat incentive coming into Wales and England, where, like the feed-in tariff for solar, they will pay people for every kilowatt hour they generate from renewable heat sources. So this is going to be another driver towards low-carbon buildings. The only problem is it stops you going for zero carbon in the design, because now you get paid for heating your building. So I'm not sure whether they've thought it through. So what you want now is a leaky building and a big biomass boiler. So, but I'm sure they'll rethink that a little bit. We've been involved in integrating renewables into low energy buildings for some time as well. This is a building that we designed in the school again in around about 2000, 2001, and it won an RIBA award, design award in 2002. It was the first BREEAM excellent factory industry building in the UK. And BREEAM is our version of LEED. I guess you've all heard of the LEED system. What's interesting is it integrates solar PV into the building fabric. So the solar PV cells also provide shading. That front pop-up on the design is the office block. And because it faces, the client wanted it to face the entrance, faces due south. There was a danger it would need to be air conditioned, even in Wales. So using shading helps us to avoid using air conditioning, and the shading also generates electricity. So it's a way of offsetting the cost of renewable energy if you can use it as an element of the building construction. This is a building that we worked on as building physicists in Switzerland. It's the first zero, I think they call it the first zero energy office in Switzerland. It's in Zurich. It's an office development around an atrium, and the facade has been designed such that these diffused glass shades, they move as the sun moves. So they let the daylight through, but they keep the solar heat. The insulation levels of the facade, it's like a double-skin facade, I guess, because the diffused shades are external. And so any solar radiation is just convected away. And the insulation levels are very high. The U values of the wall around about 0.2. And also the internal finish of the wall is an absorber of moisture. So it stabilizes the moisture levels as well as reducing heat loss. The glazing U values are around about 1, triple glazed. The atrium itself has a double skin roof with a shading device that can be pulled across. And so it keeps the solar heat at high level. And then it ventilates. It ventilates naturally in the night. So the air comes through the offices into the atrium and out through the roof. Whereas in the daytime, it flips to a mechanical system, and air is drawn through about 80 15-meter length pipes, and the air is cooled in the ground. So we get about 8 degrees of cooling in the summertime. And in Zurich, it can maybe peak at around about 35 degrees in summer. And that's enough, because we cool in the building down at night, and the concrete ceilings are exposed to the space. So we use the fabric of the building to soak up the cooth in the night, and then we cool the air coming in the day. And with these sort of buildings, the air temperature can go up to about 26, 27. And because the surface temperatures are quite low, maybe 3 or 4 degrees lower, you can get comfort. So it changes the way you start to think about comfort. So you're not controlling air temperature, you're controlling on environmental temperature. And it's the surface cooling that's really giving you the comfort. So the building doesn't have a heating system, it doesn't have a cooling system other than this. It gets a bit of heat recovery from wastewater, and also some industrial process nearby. And it's got solar thermal and solar PV to provide some heat and some electricity. That building was designed in 2003, and we worked on the simulation of the sort of thermal performance of the building to make sure that we could get comfort levels without these sort of systems. Because it's a big risk for the architect to say, right, I'm not going to put a heating or cooling system in this building. I'm going to rely on natural cooling and heating. And we did the simulations in 2003. It took a long time to build this building because it was more of a research project. The building was occupied in 2007. And the temperatures that we predicted were more or less, they were almost identical in the hot weather. When the temperature outside goes up to 35, the temperature inside gets up to 26 or 27. And in the winter time, it's so well insulated that it flatlines really, the temperature. And we simulated that, you can see at the bottom there, and then the measure. The only problem is when the building is unoccupied, say for Christmas, when people are out for a week. The temperature slowly sort of comes down. You have to pump it up a bit before the people come back in. But it works really well. And when you go there and you talk to the people, they think it's a very comfortable building. The performance of the building compared to buildings in Switzerland, on the right-hand side there you've got the red, which is the heating, the blue, the cooling, the green, the electrical power. The grey is the embodied energy in the building construction. And we can see there are various categories of performance in Switzerland. There's Minergy, which is a low energy performance, and Minergy P, which is low energy and renewables. And on the left-hand side, you can see that hardly any heating or cooling, the electrical consumption down considerably. But the grey energy is round about the same. This would be over a lifetime, say, of 30 to 40 years. So now we're in a situation where the energy we use to operate the building is equivalent to the energy we use to construct the building. And you sort of question then, maybe now we should be looking more at the embodied energy than the operating energy. Maybe that's the next sort of target. We've looked in Europe at a lot of facades. These are buildings that we worked on, double skin facades with various shading devices. The first one is the newspaper headquarters in Zurich. This is an exhibition hall in Hanover by Thomas Herzog. This is a headquarters at Hanover by Thomas Herzog. All layered facades with blinds of various forms. Either the blinds are on the outside, or they're between layers of glazing. You shouldn't have them on the inside because when the sun is in, it's in. So it's not a very good idea to have shades on the inside. Different types of shading, and very highly glazed buildings because we can get really good daylight in these buildings. The thermal performance of the glass is very good. The U values are now well below 1. We can control the solar radiation. So highly glazed buildings are perhaps not a bad option. I guess there's the embodied energy to think about, but we can now have low energy buildings which are highly glazed. And also starting to use the facade to collect energy. This is our Sustainable Building Envelope Centre in Shotton, North Wales, which is in partnership with the Welsh Government and Tata Steel. And here we develop ways of using the envelope to collect both thermal energy and to generate electrical energy. And some of the products below, the one with the arrow, that's a solar thermal wall. It's a cladding system, and that green area is a double layer of cladding, and that facade faces south, and the air comes into that, and it's preheated for the building. And these are quite successful, quite low-cost systems, and when they've been measured over the period of a year, they can provide typically 50% of the heating load of the building. And we're also looking at solar PV, how we can encapsulate solar PV, thin film PV, and onto metal cladding. So the whole roof becomes a solar generator. So we're looking at buildings as power stations is the sort of what we're trying to sort of push there. And of course, when you start to collect this renewable energy, you have to start to think about storing it, both electrical and thermal. And one of the areas of interest to us, which we're looking at the Sustainable Building Envelope Centre, is different ways of storing energy. And this is just an example of the size of a storage vessel if you wanted to store heat for this sort of office development. But you can reduce this size significantly if you start to use phase change materials and chemical storage. And we're now estimating that you can get that volume down to a tenth of what it is there. So you start to get down to volumes of storage for inter-seasonal storage that are quite viable on these building developments. And I mentioned earlier surface cooling and heating. There's a push now towards decoupling the cooling or heating from the air system and dealing with that separately through surface heating and cooling. Then you only need to provide ventilation air. And you can do that naturally, but you can do it mechanically. And then the heating and cooling is done by usually the surface of the ceiling. Either pipes in the concrete, you expose the concrete, or by panels, metal panels with tubes to take the fluid through. So some good examples of what we can achieve. But we come across real problems when we look further afield. And I always like to show this. This is Dubai in 1989, 2 years after Brundtland, if you put it into perspective. That's 2 years after we recognized sustainability as a problem. And this is Dubai in 2005. That's Sheikh Zayed Road for anybody who's been there. So what do we do about this problem? And since 2005, there's another little building that's just gone up down the road, which is the Burj Khalifa, which is 840 meters high, currently the highest building in the world. So can we sort of address these sort of projects? And that's something that we're particularly interested in at the moment. How do we do that? The first building of this sort of scale we looked at was with Atkins. About 4 years ago in Dubai, we did the building physics on this. And it's the first, it was going to be the first low-carbon tower. It's a tower of around about 600 meters, so pretty high. And the client wanted to reduce the energy use by 65% and the water use by 35%. And we looked at the usual things, that the formula I showed earlier on, reducing the loads, looking at the facade, keeping the heat out, and then renewable energy and efficient systems. And with this sort of combination, we were able to get this reduction in energy use. They started building the construction, they dug 5 basements out, then the economic crash came, and the whole thing stopped. They filled the basement back in. But I was in Dubai recently, and I think it's starting to, they're starting to turn some of these projects on again. So we think that this one might be going. Whether it's going to be going with the design that we came up with, we don't know. So that was an interesting exercise. You can get these buildings to be more efficient. You could always argue that these are not sustainable. You shouldn't be doing this in the first place, but we do these buildings. You can't get away from that at the moment. So we should be trying to do things more efficiently. And this is a building that we were recently involved in, and we brought into this to really look at how it works. It's a very complicated building. It's the first, I think, LEED Platinum building in China. And it's a mall, it's 3 floors of mall, or 4 floors of mall. It's got about 10 floors of offices and a boutique hotel on the top. And it's really a development which has this climate covering on it, and that's a double glazed facade. And it's not heated or cooled inside. And the idea is that it just tempers the environment. So when you go in there, you don't go into an air-conditioned mall. It's a naturally ventilated mall. And the offices themselves, if they want to, they can naturally ventilate to the outside into the mall. And there are lots of different options for naturally ventilating the offices. It uses free cooling at times when the conditions are right. And then it can go into an air-conditioned mall. So it's quite an interesting building, but very complicated. And at the moment, we've been appointed to write up how the building works, because it's a huge building. It's cost £200 million. And the other interesting feature about it, the developer, who is obviously very wealthy, he's put £800 million worth of art in the building. £800 million of art. And there are Salvador Dali's all over the place. The building's open now, and you can go up and climb over it if you want. So it's a strange building. This is another interesting building. It's the Bahrain World Trade Center, and it's the first real high-rise building, I think, to have significant wind energy integrated into it. It's got 3 wind turbines, and each of those generates about 300 kilowatts. So it's about a megawatt altogether, and that provides about 10 to 15% of the electricity needs of the building. The building itself isn't particularly energy efficient. And this was designed again by Atkins. We weren't involved in this, but we worked quite a lot with Atkins in the Middle East, so we know a bit about this building. It was a very complicated building to design because these towers move, so the bridges that hold the wind turbines had to be flexible. People couldn't visually, you couldn't see the turbines. You weren't allowed, otherwise you could have problems of vision, and you shouldn't be able to hear them. So it was quite a complicated building. And at the time, when they constructed it, it was against the law to export energy into the grid. So they built this thing, and then they discovered that they couldn't push the energy into the grid, because this size of power you can't really use directly in the building very easily. So they had to change the law to allow the energy to be put into the grid. But now it's working, and the towers themselves are shaped like sails. And the idea is that the wind at the bottom, the speed, as the wind accelerates into the lower area, it's the same speed as the upper area. Okay. So, as a result of all this, this is a bit of an advert now. We've set up a new master's program at Cardiff, which we're going to launch next year on urban eco-buildings. So we realised working on some of these buildings, there's very little, there's not many places you get trained to actually to deal with these sort of size of developments. So we want to put together a master's program for architects and engineers to gain a better understanding of the issues associated with these large developments. I want to finish on urban scale, and in particular looking at modelling, because for the last 10 years we've started to become interested in taking the low carbon agenda from the building to the urban scale. And we started by looking at existing buildings, because in the UK, something like 80% of the buildings that will be around in 2050, this is when we want to get to this 80% carbon reduction. About 80% of the buildings that will be around then already exist. So new buildings are important, especially in places like the Middle East and China, where they're a bigger proportion. But really, we need to start to deal with our existing building stock and to see how we can reduce the energy. And we started to develop GIS, Geographical Information System, modelling to be able to take a whole city or a local authority and to map out the energy use on a building by building and look at the CO2 emissions and then to identify packages of measures that we can apply to reduce the emissions to particular house types, perhaps. So the local authority has a limited amount of money. We want to identify those houses which are using the most energy, and then identify the most appropriate package of energy-saving measures to apply to those houses. So it's like a planning tool which enables us to quickly assess the best ways of dealing with this. And we're now using this model on a number of major retrofit projects in Wales. There's been a lot of investment in retrofitting in the UK. Our utilities, our energy supply companies, are obligated to put money back into improving the quality of housing, and in particular, the quality of housing in lower social groups where fuel poverty is a real problem. So there are big chunks of money available, and we've been using this model to help direct it to the most appropriate places. So that's existing. We started the urban scale looking at existing developments and cities, but then we started to become interested in new developments. And of course, a lot of these are in outside of the UK and Europe. China, the Middle East are the main areas. So we first looked at a development in Tianjin. We worked with Tianjin University. That's the top left there. It's a new business district. And we simply used our models, our energy models, but at urban scale, to map out at a very early stage in the master planning what the energy use is and what we could do to reduce it. You know, what's if we improve the insulation standards or whatever. Looking at a set of measures that we could apply to get achievable reductions. Another project in Qatar, this was an island project, where the client wanted to reduce the energy demand by 50%, really because he didn't have the infrastructure. The supply infrastructure didn't exist, so to keep the supply infrastructure down, reduce the demand. And then we set up a design guide, and the developers coming in to develop the individual plots then had to follow this guide. And similarly, we worked in Ras Al Khaimah, which is another one of the Emirates, on this city. And that was looking at a whole city at a very early stage and applying our kind of energy models and looking at what would happen if you change the construction type, if you use overshadowing of one building by another to reduce cooling loads, and looking at orientation of buildings. So we looked with varying things, and then we can come up with a set of guidelines for the planners to take on to inform the planning process. And another project in Hanoi, a very dense project that we did with Haider again, to look at how would we deal with a city of 100 years' time, a very hypothetical thing. So with these developments, what we want to do is to be able to set aims, to set targets, to say within a project, what do we mean by sustainability, to define sustainability at the start, and then to have an evaluation process that evaluates the project against these targets as it proceeds. So it's really, because a lot of projects, they say they're sustainable. We've got lots of eco-cities, but they don't really define what they mean. And then when they come to assess it, they have nothing really quantitative to assess it. So we need these evaluation processes. And we've been developing our modeling in this particular area using SketchUp. We now have our energy models linked into SketchUp to predict not just the operating energy, but we're starting to look at the embodied energy and the materials and the structures, and also the potential for collecting renewable energy. This is a project that we did about 2 years ago. It's Barnum. It's a low-carbon development in Chongqing in China, and we come in at a very early stage of the model. So we build our model in SketchUp. We then link that to our energy model, which is called HDB2. It's an energy model that has been around for some time. It automatically sends all the data from the buildings into our energy model. That does all the calculations and sends it back into the SketchUp environment. So we have a user interface, which is SketchUp. That provides the database, which sends the data to the simulation tool, and then we get the results. So this has been quite an exciting development for us, and it can be used to provide information very early in the design stage, again to inform the design, concept sort of stage design, because unless you do modeling at an early stage, the impact is not going to be that great. Once you've designed your building or your development, and then you do the simulation, and you say it doesn't work, nobody's going to be interested. If you say it works, then they're happy. But if you say it doesn't work, then it's very difficult to get people to change. So you have to bring this modeling into the early concept stages. And not only can you look at the whole development, but you can pick on individual buildings and see how their performance changes. And one of the neat aspects of the model is being able to do shading analysis. So within the SketchUp environment, we can calculate the shading of every facade within a development. The shading, not only by buildings, but if there's trees, we can look at the shading from trees, or even topography. Because when you put this into Google Earth and SketchUp link together, and it automatically can calculate the shaded mass from mountains or whatever features there are. So this is really useful because it helps us understand the energy performance of buildings in the context of their surroundings. And when you look at cooling loads in particular, if you just model a building on its own, it'll have a cooling load. If you put it within a built environment, the cooling load is probably going to be a lot less because the building is shaded by its surrounding buildings, especially in these dense environments. And also we can predict where, if we want to collect solar energy, because we know how much solar radiation falls on every facade within the development. And then that takes us into, how do we deal with these dense environments? And we're now starting to become more interested in the urban environment, the urban heat island, how we ventilate our cities. And it's really looking at the city almost like a building. The city becomes a building. It needs to be ventilated. It needs to have its pollution taken out. It needs to get rid of the heat. It needs to be cooled. We need to collect maybe energy across the envelope of the urban sort of fabric. So we start to think of the urban environment as a building in itself. And we're developing our modeling now to deal with not just the solar shading, but also to deal with temperatures and breezeways. In a number of dense cities now, you have to understand the breezeways. It's part of the planning process. You have to analyze the breezeways through the cities. In Hong Kong, for example, if you want to build a building, you have to demonstrate that you're not interfering with the breezeways through the city, so you don't create stagnant, polluted areas. And we've started to do some work in this area as well. This is a development in Miami where we've been looking not at the internal environment, but the outside environment, and analysing, trying to have an outside environment in this shopping area which isn't air conditioned, which is a naturally treated one. It's got a big solar shading device on the top, and we're encouraging breezeways through the development to provide some cooling. And then vertical zoning. When we look at the city, we can start to think about how we zone vertically for sustainable development. Below ground with transportation and energy storage, then at ground level, the public realm, green areas, and then at ground level. And then at roof level, we can start to collect energy and even start to create gardens and green areas and collect water, for example. So we can think of zoning the urban fabric in terms of different aspects of sustainability. And then we're now sort of looking at expanding out to a regional scale. And this is some of our current research, where we're starting to try and understand how the urban and the rural link together, how the flows of energy and people affect sustainability. And we have a project where we're looking at a more systems approach to energy. There's a lot of attention to smart grids now in Europe and smart living. So we try to provide energy to houses so that they're metered and everything is controlled so that we use as little as possible energy supply from the big generators. And we integrate our renewable energy in an appropriate way. And of course that needs storage as well. And one of our projects at the moment is looking at supply, storage and demand at this level, but also down to an individual house. And in this case, we're looking at retrofitting houses to be almost as much as possible off-grid. So we're looking at DC systems. PV, wind can provide DC electricity, Most of the time we invert it to AC because most of our houses are AC. But a lot of equipment now is available that is DC, LED lighted. We can even get refrigerators and other equipment, TVs, for example. Everything is inverted back. So we can cut out the inverters, save a lot of money and a lot of energy, and then have integrated storage with it. So we store the DC, and we have a DC system in the house, DC supply from our renewables, battery storage, and we're starting to think about being as off-grid as possible. So this is one of our new projects, and we have 10 houses that we're going to install these sort of systems in to see how they work in practice. So, I just wanted to finish off by perhaps thinking differently about how we approach sustainability. And in the past, I think we've been very negative about it. It's always been zero energy, reduce, minimize. It's been bad news, really. And individuals find it difficult to know what to do. What can I do as an individual person? So maybe I ignore it. It's something I can do. But we like to change the message, I think, to more positive. That it's not about low carbon or low energy. It's about a healthy environment. It's being productive, clean, feel good. There's a huge amount of industry associated with sustainability. So it's a huge economy ready to be tapped. It's socially supported. So it's all good news, and it's low carbon or low energy. So what we're trying to do is to lead with a more positive way in the low carbon agenda and sustainability. So thank you very much.
Two switches on, very impressive. So Phil, we have a few minutes for questions. And does anybody have questions for Phil? Hari, here, let me hand him the mic.
I think everyone here. Okay, some of the problems we have around here is humidity. So we tried to bring the fresh air into the house, but it has 90% or 80% relative humidity or water coming inside. So therefore, that's what cuts it off. So what are some of your solutions that you can deal with when you're thinking about humidity?
For natural ventilation, or?
Yes.
Yeah, I think, well, natural ventilation is, if you've got high humidity, it's difficult. I remember once we did a project with Ken Yen in Malaysia, and he wanted a naturally ventilated office block. And so we helped with the design to get the air moving through. And in the end, he air conditioned it. I think but if you can mechanically ventilate at low levels. And when I talked about the chill ceiling, a lot of people often say, well, you can do that in Europe, but you couldn't do it where the humidity is high. But really, if you've got a well-sealed envelope that doesn't leak too much air, and you can control the humidity of the small amounts of ventilation that you might be putting in mechanically, then there's no difference to here or Malaysia than Europe. So I think you can do this. You can use these technologies anywhere, but you have to think about. You have to appreciate the particular local problems.
First, thank you. Thank you for coming to Boston. And since you have done like 20 to 30 years research on this kind of stuff, and I'm wondering, have you ever go back to re-evaluate any project in practical level? Like, the example you showed about in China, in Asia, in other places, are pretty new projects. I'm just wondering, like I visited Portland. Last year we had a field trip there. Portland is famous for sustainable development, and there are a lot of LEED certified building projects. But one of the apartment we visited, the manager told us it's not that, the cost, like the operation cost, is still much more than it's saved. And so I'm just wondering, like from the market standpoint, also from the the energy consumption point, have you ever evaluated what's really happened?
So post-occupancy evaluation?
Yeah, we've done that in the past on a lot of buildings, and but most of the buildings I've shown are real projects where I guess the post-occupancy has been that nobody has sued us. You know? We've never had somebody come and say this building doesn't work, or it's using more energy, or it's uncomfortable. With these, in particular in Switzerland, where most of the buildings that I've shown that have been there for some, the China and the Middle East are new. We've been working in Switzerland probably for 15 years on these sort of buildings, and we've never had issues there. However, in Switzerland, the standard of workmanship and the quality of build is excellent. In other parts of the world where the quality of build is not so good, there may be problems. But there's no reason why these technologies should cause any more problems than existing technologies. In fact, it's probably going to be better. Because the existing way of doing it, if you're looking at commercial development of the traditional all-air air conditioning system, they have problems anyway.
But in another way, it's just like to me, it's more like a selling point in how the energy efficiency can save your money. But is that really what happens?
It's not just energy efficiency. I think with these buildings, there are a number of. If you take the standard solution that we've been looking at, really, which is take care of the facade, control the sort of radiation, reasonable insulation, decouple the ventilation from the heating and cooling, and maybe that needs active surface cooling, or it could be passive surface cooling. And if you use those technologies together, they provide better comfort. They're usually healthier because you're not recirculating air, you're just providing fresh air and exhaust and air. You usually have more floor space to use because you can work right up against the facade because the solar gains are controlled. The floor to floor height is less because you've got less space for ductwork. And in some buildings, for example, the SOM building in Guangzhou, they created another 5 floors by using this sort of system because the floor-to-floor height was less. Now, economically, that's huge in that sort of development. So there are lots of plus points about this approach. It's not just about saving energy. It's about creating better environments.
We got a couple other questions for you. Sorry.
Well, I was curious if there's another school of thought that's emerged here, and I don't know if it's concurrent there, and that is that we're not going to achieve critical mass in sustainability. We don't have the political will to do it. The commitment to wealth building is too huge. The commitment to, in all countries, that want to have an ecological footprint just like our own. That a better alternative strategy, at least for the short term, is to deal with design for resilience rather than dealing with design for sustainability. And I was curious, in light of that, if there are colleagues that you're working with who are dealing with resilience as at least an interim strategy until we get through a whole bunch of disasters that may actually lead us into acting more sustainably.
Yeah, it's taken us 200 or 300 years to wreck the planet, isn't it? And there's no way we can turn it around in 10 years. And it's taken a collective effort to wreck the planet. It's not just, it's everybody's responsible. And I think, is it Bruno Latour, the French sociologist, said that there's a real disconnect to the ability of humankind to cause this havoc and the inability of it to grasp the situation. I think we will have problems. We we will need to adapt to the climate change that's going to happen. And resilience is something. But you don't see it at the moment. You know, it's not as, it's rarer than mitigation. We seem to be designing more efficiently and for better comfort and better health, but we don't see very much any design for adaptation against climate change. So it's an area that perhaps we need to get more involved in. I don't know if your experiences here.
Hi, Phil. I have a question. So I saw you have some projects in China. Have you ever been to China?
Yes.
Okay, so you must know more about China. And as China is growing, it seems like everything is growing except the environment. So could you talk about how China could achieve a sustainable future? Yeah, thank you.
I think China the government is quite committed to low carbon agenda. I think it's got targets set, and I think the development has cooled down a bit. Maybe up to a year or so ago, it was really fast track and everything was going up. The government, I think, put the lid on that. And now there's a new government. They're sort of starting to, I think, look closely at how fast they allow development to go. So I think there's two things. One is it's slowed down a bit, which will give more time to do something. But there's an increase in attention to low carbon. We just had a project funded by the Chinese government with Tianjin University of about £1 million for low carbon built environment. So I think and I think the new government is more committed than the previous one to the low carbon agenda. So I'm sort of positive. And of course China needs it because it can't just keep on building power stations. It's got to sort of reduce the amount of energy that's being used.
So please give Phil a hand.